Okay, now that you've seen it, I gotta move my paper around a little bit apparently. Now that you guys have seen what a residual plot is, I wanted you to check out two problems and just answer whether least squares regression line was a good fit for the data or not. Okay, so here I'm gonna bring the book into the play. Number 3, Mac and Nick collected data from a random sample of students at their school to see if they could use a linear model to predict y, a student's grade point average, from x, the number of text messages a student sent on a previous day. Here's the residual plot for the model. Use it to determine whether the regression model was appropriate. Was the line a good fit? That's what it's asking. This isn't the actual scatter plot. They didn't bother to show you that. They just showed you the resulting residual plot. So they're asking, was the line a good fit? Here's all you got to look for. There's the line y equals 0. We have dots above and we have dots below, and there doesn't seem to be any kind of pattern. When you see that, we're going to call it uniform scatter. And so since it's uniform scatter, we're going to say to number 3, yes, that was a good fit. Now, number 4, move this up just a little bit. Does the grill stay hot? A curious statistics teacher wondered how fast his grill cools off once it's been turned off. He recorded the grill's thermometer reading it several times and used a linear model to predict y equals grill temperature from the time in minutes since the grill was turned off. Here's the residual plot for the model. Again, there's no way this is the actual scatter plot because that's not the way temperature works. You turn the heat off on a grill, it's not going to get cool and then get warm. This isn't the real scatter plot, this is the residual plot. So, taking a look at this, I see that there are positives and I see that there are negatives, but there's a definite pattern. For this reason, the answer to this question, use it to determine whether the regression model is appropriate. The answer is no. The line was not appropriate. The original scatter plot has to have been curved. Okay, so let's get the book out the way. And I'm going to say number 3, the line was a good fit because the residual plot does have uniform scatter. I'm going to say number 4 was a bad fit because the residual plot does not have uniform scatter. It's curved. It was clearly curved. And that's what your homework will look like for residual plots. Okay, now I've got 2 other methods for assessing whether the form is linear. 1, look at the residual plot. Here's the second one. It's called the standard deviation. The standard deviation of the residuals. Okay, and it gets a variable, it's just a s. Standard deviation of the residuals. Here's a formula you'll never need to use, but I want you to see what's going on. I'm taking the residuals. You know those are above and below the line, right? I'm taking the residuals. Let me show them to you one more time. Every time that I'm finding this vertical distance, that's a residual. Y minus y hat are all these vertical distances to the line. I'm going to take those and I'm going to square them to make them positive. Why? Because I have positives and I have negatives, and if I add up the positives and negatives, I'll get 0. So this is the same trick we used when we found the original standard deviation in this class. I'm going to take the residuals, I'm going to square them, I'm going to add them together and divide by some version of n. This time we're subtracting by 2. I can explain that some other time if you want to know. But I'm basically taking an average in here. It's the average. I'm adding up a bunch of things and dividing by how many I have. That's an average. It's the average of the squares of the residuals, and you take the square root because we squared it to make up for it. So here's the formula. In other words, that formula is the average of the squares of the residuals. So guys, it's an average distance from the points to the line. That's what it is. So hopefully you guys are picking up by now. When I keep telling you interpretations, those are things you need to know really well for your test. Interpretation, when using the line, the least squares regression line, to make predictions, we are off by an average. We miss by an average of s units. That's how you interpret the standard deviation of the residuals. Here's another way to say it. The average, I misspelled it, the average distance that data points are away from the line, the average distance points are away from the line is s units. That's what s is. You won't have to find it. We're not going to do it on the calculator. You're just going to be given an S. You're going to be asked to interpret. That's what it is. It's the average distance that points are away from a line. Okay, the other one. The coefficient of determination. That sounds fancy. Coefficient of determination. Okay, that's r squared. In order to do that mathematically, you take r and you square it. That's it. It's r squared. Okay? In other words, r squared is literally r times itself. Okay, I think you already knew that math. Here's our interpretation. I'm going to put an asterisk and an asterisk, and I'm going to tell you, I'm not going to say this to you very many times ever. This is just a phrase you should memorize because I just want you to recognize it when you see it on the test. It'll be part of a multiple choice question maybe. The interpretation goes r squared, written as a percent, not a decimal, is the percent of the variation in y, in the y variable, that is explained by the least squares regression line of y on x. You guys are probably going to want to just ask me to explain what that means. And I can give you a visual. I could explain it here if you want. Here, I'll go real quick. I'm going to draw a scatter plot, okay? And I'm going to make it kind of a weak scatter plot. It's a weak linear scatter plot. And I got this line that goes through. Okay, look, there's the minimum y value. See, that's the smallest y value I have is right there. So I'm going to call that y min. And then I'll go up to the biggest y value I have, and there's a y max. So when we collected data somehow, we got y values that went from this value all the way up to this value. So there's a variation in the y variable. It goes from this to this. There's no bigger y value, no smaller y value in my data. This is how much the y value varied. So if this was GPA scores for you guys, somebody in the class has the smallest GPA and somebody in class has the biggest GPA. That's how y varied. Okay, so I'm using r squared to answer the question, why, when I took my data, did y vary that much? And how we're trying to answer it is because x varied. The x went from here to here. That was my x minimum and that was my x maximum. And I'm trying to say that because of this line, when I got bigger x's, that's why I got smaller y's. And when I got smaller x's, that's why I got bigger y's. There's an association here. So this is what r squared means. It's a percent of the fact that this varies that's explained by the line we used to describe the association. I really don't think that helps that much, me saying that. It's a weird concept, and you don't have to rephrase what I just said or even really fully process that. You've got to take this line and realize when you see these words put together, they're talking about this percentage r squared, okay? So don't overthink that and don't over worry about it. I just want you to be able to recognize it. So I'm going to go to the next page here, the last page. And you guys can see what I'm getting into. I want you to go to your book and do number 13 on page 158. You got 2 interpretations to try. You got to find S. Let's see how well you do with this, and then I'll give you your homework.